My talk will be an enhanced mode, gallium nitride, FEG-HEMT, that means hybrid ferroelectric charge trap gate stack device for power switching application. So basically, it's a gallium nitride power switching device with a very different gate stack. Okay, so this talk will including the introductions, the material, the device fabrication, and the novelty of device technology, and then I'll demonstrate some real application for this kind of device, and then go to conclusions. Yeah, and first we'd like to introduce a bit about the material. Gallium nitride had very high mobility and high energy bandgap, which make them good for power device and for high frequency applications. So, so in this talk, we'll focus on the high power application, but also because the high mobility issue, the material can use for high frequency for power application. So that will reduce the size of the modules. Okay, the high electron mobility transistors, which I can give a little introduction. The material is usually formed by air gain and gain, and due to the band discontinuity, there's a 2DEG formed, okay, due to the band discontinuity at the interface, okay, and that one allow electron to be driven to the interface, and the interface form quantum well, and this electron can move in the quantum well without scattering and give that a very high mobility. And beside of that, the material gallium nitride have high spontaneous polarization, and also because the two material had very different crystal size, so they have a form stress at the material itself, and that also form ferroelectric effect. So electron, due to this two polarization, there's an electric field formed at a crystal. And the direction is drift the electron to the 2DEG, that enable electron to move in the 2DEG with a very high mobility, and that form a very high current transistors. Okay, so just like I said, the material have a spontaneous polarization and ferroelectric polarization because of the lack of symmetry of the outside structures. And also because of high electron mobility, negativity between the two atoms. So the figure shows that how these two polarization form, and they have a electric field, okay, driving the electron toward the 2DEG area. And then also the material is without doping, because most semiconductors need doping, but this material doesn't need a doping because the surface traps form the donor stacks, and the donor stack give electrons, large number of electrons, and the electrons is driven by the polarization at the 2DEG. Okay. And because of that, the material have very high breakdown voltage and large number of electrons, so the device is very good for power applications. And because high current and high breakdown voltage caused by this material nature. So you can see the material have a very high breakdown voltage, and also the speed on is very low, okay, because a lot of electrons, okay, due to the 2DEG, okay. And this device is compared to silicon IGBT and compared to silicon carbide, the performance is very good, okay. So but again, we did a very high current and high voltage. This is really good for the power device. But then the best area it fit for is from like 50 volt to 1,200 volt. Okay, because that featured the application of gallium nitride best. At high voltage, we competing with silicon carbide. At low voltage, then you compare with the silicon MOS. Okay, so this is the best domain, not for this kind of device, okay? And right now, this material is very hard because the EV is quite, due to carbon emission, right now EV is the effort, okay? Everybody try to develop components for the EV, and the government try to to switch all the transportation to EV. Okay, so for this kind of EV, we need a lot of AC/DC or DC/DC inverter convert. So, and also for charging. Okay, so for this kind of purpose, gallium nitride is perfect for that. Okay, so there's a lot of future for this material. And then to do that, okay, for car application, okay, is for EV application, we need a huge feature. First is need high breakdown voltage. Next is ohm resistance must be low, so the switching will consume less power. The second part is normally off device because the device have to be idle when you are not applying any voltage, so that no car accident would happen. This is for fail-safe viewpoint. Okay, and then this device, this technology start with material growth. Okay, because this gallium nitride is grow on silicon to reduce the cost. Okay. And the reason for the difficult part is because gallium nitride silicon have a lot of mismatch in the crystals, because less constant is very different for aluminum gallium nitride and indium gallium nitride and on silicon. Okay, because there are a lot of mismatch, so you need to tune the stress. Okay, and usually we grow by MOCVD, and this work we mostly use the vehicle propel. Okay, and grow on silicon, and these are case used in this growth of material. Okay, and okay, so for this system we have real-time monitoring, and we have reflection to see the thickness and the growth rate, and we can manage the curvature, we give you the strain of the stress of the films, and then we have real-time temperature uniformity measurement. And usually to grow with the device with a good breakdown voltage, we need quite a huge approach. We need thick buffer. We need sometimes we need a double heterojunction buffer with air gap to give high breakdown voltage and also low leakage current. And we use carbon doped to trap the electrons. And usually sometimes with iron doped too. And then we have super lattice to trap the electrons. Okay. So so this kind of gallium silicon is right now we can do very good quality. Okay, and including that we have very uniform round to round, we have super lattice very fit, perform very well, and then we have low particle generation, good uniforms, and thickness and completion, and ball is very minimal. Okay, and electric property is excellent with mobility up to 15 to 2,000 centimeters square centimeter and per second, and high breakdown voltage and very low leakage current. So with this kind of approach and the tool, we can get very good quality for this kind of applications. And this is a typical demo. We have the initial buffer layer and super lattice and air gain and gain, and top of that we have a gain. Okay, and this give you very good performance. You can see in the letter, and then we can see that this device we use with air gain, and super lattice, we can get like up to grow on 6-inch without cracking, and the super lattice have like close to 1500 volt device. Okay, performance. Okay, and this is uniformity. We can see that the uniformity around 1% for shear resistance, 2.2% for mobility, and shear resistance is only 2.45%. Okay, uniformity. Okay, and then we give it a device fabrication. So we have mesa ohmic gate passivation, VOH, and interconnect. Okay, and this one. Okay, the things you have to watch about is the surface, so-called current collapse, and this is because the electron donate, the surface state donate electrons, and they become particle charge, so they could trap electrons from the gate, and this electron will deplete the 2DEG and freeze cause the current drift if your bias voltage is high. Okay, so that way after operation the current is getting low and low. That's called the current collapse. And then next, you can bypass this effect by using the so-called nitrogen treatment, because we use nitrogen treatment because the surface nitrogen is depleted. Okay, and then if you use surface treatment by nitrogen, you can actually reduce the leakage current. Okay. And also this switching characteristics, the same way with nitrogen passivation, with nitrogen treatment and passivation, you can suppress the degradation of a dynamic ion. Okay, and it's compared to it's only 1.04 times compared to the sample without the nitrogen passivation. And so this means that with nitrogen treatment and nitrogen passivation, this can suppress each electron trapping effect within the device. Okay, operation. Okay, and this is the layer, the tool we use aluminum nitride passivation layer. After in the surface passivation, we use aluminum nitride layer first, and this aluminum nitride layer is using plasma enhanced ALD. So you can see that with the plasma enhanced ALD, you can actually reduce the surface states. Okay, and this is actually after you use aluminum nitride, aluminum nitride, and aluminum oxide, and you can see the hysteresis over the IV curve. Okay, for the IV curve. So you can first from the TM you can see the sharp interface using this PELD aluminum nitride, and then you can see that very good stable tensor characteristics without hysteresis. Okay, and then we can also reduce the ion, which is the goal to reduce the power consumption, and you can actually glow the N-type gate nitride. With the whole happily doped gate nitride, you can reduce the barrier, and then you can form a better contact by tunneling. Okay, and this is the ohmic contact up and ohmic regrowth. You can see that the ion is greatly reduced from 5.8 ohm per millimeter to 1.74 ohm per millimeter. Okay, and then for the device on technology, we can see that this is what we want. That means for we usually need nobody off, because with nobody off, you don't have to change. You don't have an inverter to change it to 8, and that's a simple circuit. And then the power consumption is much lower because when idle, there's no current. And also it providing fail safe, because if you have a AC/DC or converter, then if it fail, then your device, your system, whole module fail, and then the car will keep on going. So this provides fail safe, okay, operation. And but with that E-mode device, you still have some requirement. For example, your threshold must be high to avoid 40 turn on, and you must remain high current and high breakdown or high power device, and you want to remain all resistance, so it will not affect your power consumption, and with low leakage current. And finally, it should be reliable. Okay, that's the most important thing. And this gives you the 40 turn on if your device is not your VTH is not high enough. If you have a 40 signal, the module will turn on, then the car will start running. So that's what we want. So we have to have a high VTH to ensure the car will not turn on with the 40 signals. Okay, and to do that, there's quite a huge approach. For example, you can use a recess gate, you can use P-GAN, you can flooring implantation. That's what people are using. And then, okay, next one, the one we propose is the ferroelectric gate material. And in this approach, the ferroelectric material is put between the charge trapping layer and the top layer. Okay, gate layer, and this ferroelectric layer will provide a polarization in the material, and the polarization will induce electric field which against the electric field you apply to the gate. In that way, you have to apply a higher gate voltage to turn it on. Okay, so that's the idea, the beauty of the ferroelectric type of get stack. Okay, so ferroelectric here is just give you a very high VTH. Okay, and the way you do is use hafnium nickel oxide, which is used as a ferroelectric material, and you can see that in the center, if it's not a combination, just hafnium oxide or nickel, they would not have this kind of a ferroelectric effect. Okay, they don't have this polarization. Okay, and this you can see that the polarization is highest when the hafnium nickel oxide is 50%. Okay, and then the amorphous hafnium nickel oxide can be turned to a single crystal. Okay, and after you you do annealing. Okay, and this is the stack that we use. Okay, we use hafnium oxide, aluminum oxide as preventing the turning over the current, and then hafnium oxide is as a charge storage layer, and finally the hafnium nickel oxide as the ferroelectric layer, and another aluminum oxide on the top. Okay, so if we just use the recess, okay, the current is not high enough. Okay, the VT is not high enough. Okay, that's next one. Device B is use the fluorine, but fluorine is not stable. Okay, and mobility is low. Only with this kind of ferroelectric stack, the device have a very high VTH, in this case 4.4 volt, and very high current. It's not affected, okay, because we're not doing remove any the aluminum nitride layers. Okay, and this is the comparison between this fluorine treatment, the recessed device, and this ferroelectric HEMT device show the highest IDS and with very high VTH of 4.4 volt. Okay. And this shows how you started. Okay, you start with initiation with VGS at 12 volt for 1 second, and you call this polarization in the charge storage layers, and then that will start to sustain your polarization. Okay, after you initiate, and you can see that after initiation, more electron is trapped in the gate oxide stack and achieving the VTH from negative to positive, and again no degrade in the current. Okay, and you can see that for all these kind of different approaches, this device give you the best VTH and highest VTH with very high current. That means no degrade in current density. Okay, and then we can also apply this to FEG-HEMT. Okay, and get low SP, okay, and high breakdown voltage. Okay, in this way we use tri-gate. Okay, and we use tri-gate as the picture shows. Okay, there's several fingers, and each finger is forming the gate tri-gate, and this tri-gate HEMT, and this tri-gate is covered by the stack we just mentioned. Okay, and this gate stack can deplete the sidewall, so the device become the E mode, because when you're not turning on, is the current is shut off, and then we have very low channel resistance by this way. Okay, and this give you the current high, current nitride HEMT using hybrid ferroelectric gate trapping layer along with this tri-gate approach. Okay, so this is actually the cross-section of this kind of tri-gate, and we have many fingers, and each finger composed of hafnium oxide, hafnium nickel oxide, and the aluminum oxide. Okay, layers. Okay, and this is the top view of the materials of the device, and you can see that there's quite a lot of fingers. Okay, each one is about 100 nanometer, and they are parallel to each other, and then you put the ferroelectric stack around them, and then you deplete every finger, and all the total finger give you the total current. Okay, you need. Okay, and this is for each finger. We have around 100 nanometer. Okay, with the gate stack. Okay, and then we have with this kind of get stack all together, we have VTH 2.61 and hysteresis very minimal with the substrate slope and high GM. So the initiation is the same for 1 millisecond, and large VTH at 5.83 is achieved. Okay, and this is the tri-gate. Okay, you can get ID over 96 milliamp per millimeter, and R is about 5.0 ohm per millimeter. And this one actually, when combined together, it gives you the R at 5.0, R channel is 2.71, and normalized is the channel resistance is about 1.01. This is the lowest, okay, published. Yeah. And this gives you the why it can achieve this kind of a 10 ohm EMO is because you narrow wire which must be below 100 nanometer to form this kind of special features. Okay, to turn it off as the E mode. And this breakdown voltage, this kind of device still remain like a 788 volt. Okay, so this one give you high breakdown, low on speed, on SP, and very high current. Okay, so this is probably the best. Okay, up to now. So we have VTH 2.1 and our own 5 volt, and our speed peak is 0.76, and breakdown is 788. Okay, and this is the increase for the dynamic R during operation, and it's only 1.6. Okay. So next we show you this kind of device we developed for RF switching applications. Okay. So this device we use is 120 millimeter. Okay. And this gives you the 60 amp at 1200 volt. Okay. And this is the device we make. Okay. And this is the device we use for some applications. Okay. Case code. Okay. And we also use for some real application in the vehicles. And this is booster converter. You can see the power consumption is much lower than most MOSFET. And also for some EV applications. Okay. And this is for power adapter. Okay. And this is solar panel inverter. Okay, we use this kind of demo device. Okay. And okay, next one is we work with the Panasonic for gate driver applications. And we use this kind of device, use a microwave as gate driver. And you can see that, okay, next one, the time is running out. And no?
6 minutes.
6 minutes? Okay, so we use this kind of device for use microwave as a gate driver. Okay. And I think one of the beauty of this kind of gallium nitride device is because the mobility is very high. So you can, the device can operate the megahertz, which is not possible using silicon and other device for this kind of power application. So we use this kind of nature for microwave driver, and then the gallium nitride itself, the gallium nitride device can go to higher frequency, and then that will reduce the size of the circuits and the modules. Okay, and this is just an example of the good part about using the gallium nitride, okay, as a gate driver. And this we use gate driver to realize high-speed operation, and then with all the circuit put together, and then you can see that the gate driver one chip, okay, put a which replace the whole module, okay, using the discrete components. And this is the size, okay, if you replace with gallium nitride MMIC, okay, and the gallium nitride devices, the reduction of the size is to 1/100th of the original size. Okay. And also we have also used this gallium nitride device for wireless charger, and this is the wireless charger we adopt. Okay, and then the device can work to like 105 meters. Okay, So this is what we demo already. The breakdown voltage 600 volt, current is 10 amp, and then we can operate at 1.5 millimeters or 1.5 meter as a wireless charger. Okay. And so, okay, 104 meters with 1 watt, and power efficiency is around 95% at 50 centimeter, and maximum power for single PTU is around 85 volt, and breakdown is very reliable up to 800 volt. And if you consider at 50 centimeter, it can go up to 5 watt. Okay. So this is what we demo, okay, with the wireless charger, okay. So overall, the gallium nitride, okay, could play a very important role, as I show many applications for power switching systems. And this ferroelectric gate, highly ferroelectric charge gate is the first time, okay, demonstrated in literature. And this shows that this could be the best performance if you compare for high voltage and the current and breakdown. Okay, the tri-gate, okay, with very sharp SS results in low channel resistance and demonstrate high VTH at 2.6 volt and with lowest R on SP for 0.76 milliohm per centimeter square with high breakdown at 650 volt. And these lowest are on reported so far for EMO devices. So this gallium nitride HEMT device shows very high breakdown of much more higher than 600 volt, and with air gain and double HF junction and low temperature interlayer buffer layers. Okay, gallium nitride HEMT have demonstrated power switching and gate driver power transfer application. And gallium nitride, all gallium nitride based power module have been realized by using NCTU gallium nitride HEMT. Okay, so that's about it. So it's open for questions.